Hello, this is the first video for Chapter 2, which will cover and discuss the chemical basis of life, paying special attention to atoms, molecules, and water. So the first portion of this lecture video series will include atoms. We will have an additional video on chemical bonds and molecules, and then a final video talking about the properties of water, pH, and buffers. So as we talk about atoms, let's first talk about something you may have heard of, which is matter. So matter is going to be anything that contains a mass. So if you're not familiar with what a mass is going to be anything that has some type of weight to it. And matter also has to be able to occupy space. So that means matter has to be able to take up room, right? It has to be able to occupy a certain particular area. One thing that comes up here as we talk about matter is the atomic theory. So we've talked about what a theory is so far, and the atomic theory is that all matter, so everything that has a mass and takes up space, is going to be made up of atoms. In particular, you may remember this from elementary school days. Matter consists of three states. We have liquids, solids, and gases. So thinking of the definition of matter, anything that has mass and contains space, I want you to start to think about a few things that have that. Okay, you might have taken your thinking cap off, and maybe you thought of some of the things that I have on the screen. So of course, H2O is a great example, a table, balloon, the individual, and the easel. Fire is matter, as well as an animal like this tarantula here. So all of these items are going to contain some type of weight to them, and they are also going to take up some type of space. Another great example of something that is matter would be air. And I know that confuses people, but if you think about it, air is made up of elements like oxygen, carbon, nitrogen, right? So all of these things are atoms themselves, and although they're very, very small, we can't see it, they still do have a little bit of an atomic mass, and they also take up a little bit of space. So something like air actually is matter. So we know matter is something that has a mass, and it also has to take up space. So think about something that is not matter. Okay, hopefully you've thought about it. If you're still thinking, feel free to pause. And these are going to be some examples of items that are not matter. So for instance, time. Time doesn't have a weight. It doesn't take up any space. Rainbows, energy, heat, memories, all those things do not have a mass associated with them and do not take up space. Therefore, they are not matter. So I've said the word atoms a few times. Let's talk about them a bit further. So an atom is going to be the smallest unit of matter. So if we're talking about levels of organization, an atom is going to be at the very bottom when we're talking about matter. So you can't go any lower than an atom if we're still referring to matter. Also, an atom cannot be broken down any further. So we don't take our atom and break it apart into other pieces. Our atom is going to be the very lowest for our matter and for just what it consists of. And each type of specific atom is known as an element. So you've heard of many elements before. Maybe you've seen a periodic table of elements. This is going to be a table of different pure atoms. And when you have two or more atoms that are bound together, that forms a molecule. So again, about this element thing. The element is going to be a pure substance. So that means if you're looking at an element of a material, it is purely just that one type of atom. There are no other types of atoms inside that element. There are actually 98 naturally occurring elements, and although we have a lot of other elements in the world and on Earth, only about 4 of them make up 95% of the mass of most living things. So if you took a human being and you analyze the atomic composition of the human being, you would see about 95% of the human is these four elements. So think about if you know what they are. Hopefully you said carbon, hydrogen, oxygen, nitrogen. I like to think of it as chone maybe. So these are going to be the 4 elements that make up a majority of your body mass. Like I mentioned before, this is the periodic table. We'll talk a little bit about how this table looks and how you can read it more clearly, but this is an example of one if you hadn't seen one in a while. So, although we can't break an atom down any further as it relates to matter, an atom is made up of different components. So when we're talking about matter, an atom is the lowest on the list, but there are different components that actually make up an atom. So these are called subatomic particles. So there are going to be 3 of these subatomic particles. The first one is known as a proton. So a proton, when we look at pictures of them, we tend to draw them in the red color. And protons have a positive charge. So the P for proton, positive. Real simple analogy and correlation there. We find our proton in the nucleus, which is the center of the atom. Think of this as the sun, and we're going to have some items that eventually are going to revolve around the sun, but thinking of your nucleus as the center of the atom, that's where you're going to find your positive proton. Also in the center of the atom, you have a neutron. Most of the time we draw that as being white. A neutron has a neutral charge. So when we talk about a neutral charge, sometimes we'll just draw this little O or this little circle. That means neutral. So that little O is going to represent neutral. That is also going to be found in the nucleus of the atom. And then the electrons. The electrons are going to have a negative charge. When we draw pictures of them, we have the black color. And electrons are not found in the nucleus. They're actually going to be found orbiting around the nucleus in the shells or orbitals. So we'll talk about what a shell and orbital is, but as you see, we have these electrons here. I'm just redrawing it so you can see it a little better, and they are going to be outside of the nucleus. They're going to be outside of that core, and they will revolve around our atom. So it's important to know this line right here. The protons and the electrons are going to always be present in an atom in equal numbers. This is very, very critical because we want to make sure our atom does not have an overall charge. So we don't want any charge on our atom. What does that mean? That means if we have 7 positive protons, then we also will have 7 negative electrons. That's going to give us a net charge of 0. We do not want our atom to have a charge. There are some situations in which we do, but naturally we do not want it to have a charge. Now the number of neutrons can vary because remember they are neutral, so they don't have a charge. They're not positive, they're not negative. So just like if you take 7 plus 0 plus 0 plus 0, it still equals 7. That's the same concept with a neutron. You can have any number of neutrons there, and I will tell you about how we calculate the exact number of neutrons that are present. So again, just kind of visualizing this for you. If you're a visual person, I want y'all to be able to see, of course, in the core, you have that nucleus, which is going to have both the positive protons and the neutral neutrons. And then floating around, you're going to see these little black dots are going to represent the electrons. So they're going to orbit around that core or that nucleus. Again, this is just showing another image. Let's focus more on helium. It's a better example. And if you look here on the picture, you're going to see, again, if we have 2 positive protons, we have 2 negative electrons. And in this case, we also have 2 neutrons as well. So helium is an example of 2 protons, 2 neutrons, 2 electrons. Okay, so let's talk about those electrons that are orbiting around our nucleus. So I'm going to give you a few concepts and then I'm going to draw it out for you in a separate slide. So just walk through this part and rewind it if you need to. Electrons are going to occupy orbitals found within shells. So they're going to occupy a space called an orbital that we find within a shell. And I'm going to draw some examples of what that looks like. So when we first looked at an atom, we kind of imagined it to look like a solar system. So like I said, you have a nucleus in the middle and you have your electrons that are going to revolve around it. However, we noticed that in that circle, in that revolution, you have some areas that have a very high probability of finding an electron. So an example I would give you would be Bowie State's campus. Let's say this circle represents Bowie State's campus. If I was looking for students and I say, I want to find some students on Bowie State's campus, where could they be? They can be anywhere on the campus, but a big hot spot for students might be the library. Another hot spot for students might be the student center, right? Another hot spot for students might be the natural science building, right? These concepts are going to be the same with our electrons. We know that although they revolve around a nucleus, there are some regions where they like to hang out. Those regions are called orbitals, and when we draw them, we sometimes depict it as a cloud. Okay, so I'm going to draw a better picture that really reinforces that cloud idea. So let's say I am drawing my nucleus, which consists of some protons, right? I'll just draw a few protons. I will also draw some neutrons, just so we have something there. And then I'm going to draw the circle around this nucleus. So we kind of separate that. The next thing I will draw will be a shell. So a shell is that orbit, right? So as the electrons move around this nucleus, they're going to move in this particular orbit in which we call a shell. Within this shell, we're going to have these cloud-like regions called orbitals. I'm going to draw a little cloud. So this would be like the library. Now, each of these orbitals that we have can hold up to 2 electrons. Only 2. If we start needing or having more than 2 electrons in our atom, then we're going to need more orbitals. Again, like I mentioned, these orbitals are contained within a shell. So in this case, the purple line is the shell, while the green cloud is the orbital. So purple line, the big circle around our nucleus is going to be the shell. That's going to be the racetrack, for lack of better words. And those pit stops, or those little clouds, we're going to call that the orbitals. So an atom actually can have many shells, right? What you tend to see is, let's say that is the nucleus. You'll have the first shell, the second shell, the third shell, that type of thing. Now keep in mind, the first shell only has 1 orbital, meaning the first shell can only hold up to 2 electrons. So that's electron number 1, that's electron number 2. So if this is a little confusing to you, then again, I would rewind it back to the slide and watch it again. Okay, so each orbital can hold up to 2 electrons. There is a rule here. We must fill the first shell and orbitals before we can build another shell with orbitals, okay? So in this picture, we have to fill the first orbital before we can build a second shell. So you see the second shell in red, we had to fulfill those first 2 electrons in the first shell. Think about going into a classroom. You know, sometimes you remember going into the classroom. Maybe there's a row of 5 seats here, 5 seats there. Sometimes you need to fill up the first 5 seats in the first row, then we can start building our second row. After we fill those seats up, then we can go to row 3, right? It's the same kind of concept. We need to fill in our orbital in our shell first before we can go to the next one. So electron shells have one or more orbitals, right? We talked about that. As long as you have more than 2 electrons, you're going to need another shell. So each shell is going to have at least one orbital. Each shell has certain types of characteristics. So the first shell has one orbital, which means it can hold up to 2 electrons. The second shell has 4 orbitals, which means it can hold up to 8 electrons. Remember, each orbital can hold 2 electrons, so if we have 4, it's 4 times 2, we got 8. For one orbital, 1 times 2, it's going to be 2. I'm not going to ask you questions about the different planes, so if you read anything about 2p, px, anything like that you may learn from chemistry, we're not going to cover in this class. We're only going to build 2 shells. So let me just draw a picture just to kind of help solidify everything. So let's say we're looking in the nucleus. I'm going to draw a little circle for my nucleus. I'm going to say 6 positive, 6 protons, 6 neutrons. So remember our rule. The number of protons is always going to equal the number of electrons. So in this case, if I have 6 protons, that means I have 6 electrons. So let's start building our atom. Let's make the first shell. We'll do shell number 1. Remember, the first shell has how many orbitals? I hope you said the first shell has 1 orbital. So we'll just draw a little cloud that will represent our orbital. Now, we want to fill up the first orbital or the first shell before we build another shell. So let's go ahead and put our electrons in the orbital. So we got 2 electrons right here. Now remember, we started off with 6 electrons. We just added 2. So now we have to find somewhere for those next 4 to go. All right, let's do our second shell. So ask yourself, how many orbitals is in our second shell? The answer is 4. So I'm going to draw the little cloud so you can clearly see what's happening here. Okay, so now we have 4 electrons. Now while we do want our first shell to be full before we go to the next, as we start adding in electrons, we want to add them one by one in a clockwise fashion. So we want to add 1 electron here, 1 here. We'll keep going around, and boom, we've done our 4 electrons. Now, the reason is we have a little more space to spread out our electrons. So in this particular case, we want to go around the atom into each orbital and drop off an electron. If we had to add an extra electron, then we would just double up. But first we want to spread out. After we spread out, then we start doubling up. So again, let's redo this with a different number. So I'm going to clear the screen now. If you want to look back at this problem, just rewind it. But I'm going to clear the screen so that we can start working on a new atom. So let me just clear it for a second. All right. So let's say we were working with an atom where you learned that there are 9 electrons and 9 protons. So again, in our nucleus, we can just write the number 9 positive, and let's say there's 9 neutrons as well. So we'll do that for the neutrons. Again, we got to build our first shell. Shell number 1 is going to have 1 orbital, And within that one orbital, we're going to be able to place our 2 electrons. 1, 2. All right, let's build our second shell. Second shell. Our second shell has 4 orbitals. Now ask yourself, how many electrons should you be putting in this second shell? So how many electrons go into the second shell entirely? You should have said, well, there are 9 electrons total. I already added 2 in the first shell, so the remaining 7 need to go in that outside shell. So let's add them. We're going to go around in any clockwise fashion. You don't have to start in one particular orbit. You just want to go around. Imagine like a school bus. Y'all remember the school bus? Everyone usually gets their own seat, and after that, you got to start doubling up, right? So now that each of our orbitals has had an electron, now we just have to start doubling up. We have to get to 7. So this is number 5. This is 6. This is 7. As you see, 1 is going to be missing an electron, and that's okay. And we'll talk about the importance of this missing electron later on. But so far, everything looks good. We need 9 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 positive protons in the nucleus. We have 9 neutral neutrons in the nucleus as well. So this is a great image of what an atom should look like. So again, let me talk a little bit about that arrangement of electrons, and I want to just introduce you to a term which is called a valence shell. So a valence shell is known as the outer shell. So anytime we're talking about electrons, the valence shell is the outermost shell. This shell is going to be the most important for reactions. That's because this is what's going to interact with other atoms. If there's another atom close by, it's going to start to interact with the outermost shell of its neighboring atom. So that's why we really care about how the electrons look in the valence shell. Okay, so we are at a point in the lecture that I want you to really pause and evaluate how you are doing. Ask yourself, on a scale of 1 to 10, where 10 being an expert and 1 being clueless, where you fall on this scale, okay? You should be somewhere around a 7-ish, 8-ish to move forward. If you don't feel very good with understanding what we just talked about, then please start to rewind this video and make sure you can try to get yourself to an 8 or 10. If you're still having trouble, then please don't forget the #1 resource is the book, and then of course there are office hours, a TA, and then there will be time for questions in lecture before we start diving into some practice questions for you. So again, if you're not sure right now, this is a great time to go back, watch it, and if you are, we got just a little bit more before this video is done. Okay, so when we're thinking about our subatomic particles, we're pretty good on electrons. We talked about electrons a lot. Let's talk about protons. So a proton, or in particular, the number of protons an atom has, is going to be what distinguishes it, separates one atom to the next. So if one atom has, let's say, 8 protons, it is going to be different than another atom that has 9 protons. This is going to be one type of element, and then this one is going to be a totally different type of element. So as we're going to change between the number of protons, you're going to get different types of elements. We can recognize the number of protons by a value called the atomic number. The atomic number is going to be equal to the number of protons and also equal to the number of electrons. It is not an addition, it is just the number. So the atomic number is the number of protons, and it is also the number of electrons. It is not protons plus electrons. It is merely the number of protons and the number of electrons. So that number will be the same. If the atomic number here is 11, that means we have 11 protons, and we also have 11 electrons. That's because, again, we want the net charge to be 0. We do not want to have an atom that's positive or negative. We want it to be 0. So if I owe you $11 and you owe me $11, then we are all good. Other examples, again, hydrogen is up top, magnesium, atomic number is 12. That means you got 12 protons, 12 electrons. So let's look at something like nitrogen. Nitrogen is represented here. And another thing to keep in mind is when you're looking at a atom on the periodic table, the top number is going to represent the atomic number. Okay? We'll talk about what that bottom number is in a little bit, but just keeping in mind the top number is always the atomic number. So in this case, the atomic number is 7. That means we have how many protons and electrons? You should have said 7, I hope. So let's say we had to fill those up. We would put the first 2 electrons in this first shell, and then we would have 4 other orbitals in our second shell, in which we would place our remaining 5 electrons. So again, keep in mind, our second shell is not all the way full. We still have some space for an electron here. We have space for an electron here, and we have space for an electron here. This shell is full at the top, or excuse me, this orbital is full at the top. But again, showing you 7 protons, 7 positive items in the nucleus, and then also you have 7 electrons, which will be 2 in the first shell, 5 in the second shell. Again, the same way we had that term valence shell, those electrons on the outside are called valence electrons. So, what's something we haven't talked about so far? Neutron. So let's talk about that neutron. So, an atomic mass is where the neutron comes into play. That is because protons and neutrons are just about equal in how much they weigh. So if you weigh protons and neutrons, they're pretty heavy. That is compared to an electron, which is 1,800 times smaller than a proton and neutron. So these are going to be the heavy molecules, while the electrons are teeny tiny grains of sand. So because of that, when we're trying to have our mass of an atom measured, we need to look at the atomic mass. So imagine our atom had to step on a scale. Once it steps on the scale, once we figure out the mass, this is going to tell us information about the number of neutrons in an element. Okay? The way we can figure that out is our atomic mass is going to be equal to the number of protons plus neutrons. This is important because we can get both the atomic mass off of the periodic table as well as the number of protons off the periodic table, because if you remember, our atomic number is going to represent the number of protons. Okay, I'm going to give you some examples, so if that math equation is not settling in just yet, we will look at it again. So our version of pounds for atoms is known as daltons. So instead of saying our atom weighs 1 pound, we're going to say our atom weighs 1 dalton, or 1,000 daltons. I just want you to understand the correlation between dalton and that being how we weigh atoms. And then if we wanted to count the number of atoms in a particular substance, we would use the term moles. So we might say there's 1 mole of this particular atom. That's going to represent the actual number of atoms. So again, I wanted to just reinforce that idea. Again, with the periodic table, This is really interesting because I want you to understand that when you look at a periodic table, there is a lot of information here. The rows, so this is going to be going across, are going to represent the number of shells. So if we were to draw this atom is going to have one shell. That makes sense because if you look at it, it has an atomic number of 2, meaning there are 2 electrons. And remember, 2 electrons fit in our first shell. This row is going to have 2 shells. So that means we can have no more than 10, right? You have 2 in the first shell, 8 in the second shell, that gives you 10. And then 3 shells, 4 shells, 5 shells, on and on. Our columns are known as groups, and they're going to represent the number of valence electrons you have. So for instance, this second group is going to indicate an atom that has 2 valence electrons, while something in group 17, it actually is going to have 7. So you drop the little 1 in front of 17, and we're going to have 7 valence electrons in these. So our periodic table is not just a colorful way to organize our atoms, it's really telling us a lot of information. So if you look at the periodic table, you may notice that while we have our atomic numbers across the top, our atomic masses tend to have a decimal place. So think to yourself, why something would have a decimal place? Maybe you came to the conclusion that that atomic mass is actually an average of numbers. Think about your grade in any class. Most people don't have a grade like a 75. Their grade might look something like a 75.21, right? That means they're averages. Some tests you got a 100, some tests you got a 50. All of that is going to play a role. So what do we call atoms that are the same but are a little bit different? That's an isotope. An isotope is where you have the same number of protons. So we're still talking about the same element, because remember, that is going to determine the element, but we have a different number of neutrons, okay? Remember, neutrons are 0. So it's like the difference between 7 plus 0 plus 0 versus 7 plus 0 plus 0 plus 0 plus 0, right? Yes, the zeros don't change the outcome of it being 7, but maybe you use more paper when you have more zeros. Maybe it takes more energy when you have more zeros, right? All that kind of stuff. So if you have an isotope, that means you have the same number of protons, but a different number of neutrons. So again, that atomic mass that you see on a periodic table is averages because the mass, remember, is made up of both the number of protons plus neutrons is going to give us our atomic mass, and that is going to be a variable, right? So that proton number will stay the same, but depending on which version of or which isotope of the element we're talking about, the number of neutrons can be different. That's why sometimes you have a rounded number. If you were to ever see a rounded number, make sure you follow the normal math rules. So if it's 0.5, then you want to round up to the nearest whole number, right? If it's under 0.5, so 0.49 or lower, you want to round down to the nearest whole number. So I'm going to give you a few examples. So let's look at this particular atom here. So this is some information I want you to look at. Number 1, the element name. Sometimes you may see the element name across the top, but think to yourself, what is that first number, the number that's on the top? What term is that? And what is that representing? All right, I hope you said the atomic number, which represents the number of protons, and it represents the number of electrons. The atomic symbol will be in the middle, and then the number at the bottom. Ask yourself, what is this? And again, what information does it tell me? The bottom number is the atomic mass. That's going to be how much this weighs. And remember, our atomic mass is going to be the number of protons plus neutrons. So if you had this question and I said, tell me the number of protons, electrons, and neutrons in this particular atom, you would say, well, The atomic number here is going to tell me the number of protons and electrons. So I can answer that by saying protons are going to be 42, electrons are going to be 42. Neutrons, that's where it gets tricky. You have to ask or tell yourself that atomic mass is the number of protons plus neutrons. So now we just do some math, plugging and chugging, and see what we know. I'm giving you the atomic mass. You're going to put that number there. I'm also telling you the atomic number, which contains the number of protons. You're going to put that value there. So realistically, you're going to have 95.94, which again we said we would round up. So that's 96 equals 42 plus n, solving for n. So we subtract 42, running out of space. 96 minus 42 is going to be 54. So our number of neutrons in this case is 54. Now, I would only ask you to give me the values for something like this. I would never ask you to draw this picture. So I'm not going to have you draw 42 electrons, but I would expect you to know how to calculate the values for something like this. So again, this is something we can do in class, but if you pause this, I want you to see how well you could draw an atom that contains the location and number of protons, neutrons, electrons. Tell me where the nucleus is, indicate what parts are positive, neutral, negative. Make sure you draw your clouds. We will do this in class for practice, but you're more than welcome to pick an atom, let's say carbon here, and see if you can identify the number of those protons, the number of those electrons. Can you draw it the way we did before, where we put something in the nucleus and we started drawing our shells with our orbitals? Can you do that? We're going to practice that in class, but this is going to be the end of the content for the lecture. So again, if you are confused in any way, remember our scale of clueless to expert. It's totally fine to be at any number, but I want to get everybody to about a 7 or 8. Hopefully it's a little bit higher as we start putting information together. If you want to review this again, this is a great idea. If you're also stuck, feel free to read the book and look forward to the next part of this lecture.